Today, we are diving into the concepts of RAG, or Retrieval Augmented Generation, to build more accurate, reliable, and useful AI applications. By applying RAG, we help companies and customers improve user satisfaction and save them the time by ensuring correct AI output. This video is for anyone who's working on AI adoption. Whether you're a developer, data scientist, product manager, or executive business leader interested in AI, you will have a solid understanding of RAG as a powerful technique. We will learn about core RAG components, its architecture, and different types of RAG approaches that enhance LLM results using the data the LLM wasn't trained on. By the end of this video, you will be ready to improve accuracy of LLM output with your custom data. Retrieval Augmented Generation, or RAG, is a technique that enhances large language models by connecting them to external knowledge sources. It fundamentally changes how large language models interact with information. Instead of relying solely on what LLM was trained on during the training phase, RAG enables models to retrieve and use external information at inference time. At its core, RAG combines the two key capabilities: retrieval of relevant information from a knowledge base and generation of responses using the retrieved information. Standard LLMs are like closed book exams. They can only use what they've memorized during training. RAG transforms this into an open book exam, where a model looks up specific information before answering. Large language models, despite their impressive capabilities, have several critical limitations. They are limited by the knowledge cutoffs. GPT-4 was trained on data up to a certain date, and it has no native knowledge of events after that date. This means it can't answer questions about recent events without additional context. LLMs have no access to proprietary or private information unless specifically fine-tuned on that data. Our company documents, personal notes, or specialized knowledge aren't part of their training. LLMs tend to hallucinate, generating plausible-sounding but factually incorrect information. This happens because they're predicting what text should come next based on patterns, not because they're retrieving factual information. LLMs lack transparency. When they generate an answer, we typically don't know where that information came from or if it's accurate. RAG directly addresses all the limitations by grounding LLM responses in specific, retrievable sources of information. Every RAG system consists of three essential components. Knowledge base is our external data source. Documents, databases, APIs, or any other information repository. This data is processed, chunked into manageable pieces, and indexed for efficient retrieval. The retriever. This is the component that takes a user query, searches the knowledge base, and returns the most relevant information. The retriever typically uses vector embeddings and similarity search to find information semantically related to the query. A generator. This is the LLM that takes both the original query and the retrieved information to produce a final response. The generator needs to understand how to use the retrieved context effectively. With these components, we need to understand the typical RAG workflow. Data preparation is when first documents or data sources are broken down into smaller chunks. These chunks are then converted into vector embeddings using an embeddings model. These embeddings capture the semantic meaning of the text and are stored in a vector database. When a user asks a question, the query is also converted into a vector embedding using the same embedding model. The system searches the vector database for chunks that are semantically similar to query embedding. This is typically done using techniques like cosine similarity or approximate nearest neighbor search. The retrieved text chunks are combined with the original query to create an augmented prompt for the LLM. The LLM generates a response based on both the query and the retrieved context. The model now grounds its answer in specific information rather than relying just on its pre-trained knowledge. Some advanced RAG systems include additional steps like re-ranking retrieved results, filtering for relevance, or additional citations to sources. This process happens in near real time, giving users the impression of interacting with an extremely knowledgeable AI that has access to specific information sources. What makes RAG really powerful is that it doesn't require retraining or fine-tuning the underlying language model. Instead, it extends the model's capabilities through this retrieval mechanism, making it more flexible and adaptable to different knowledge domains. Next, we will take a deeper look at the RAG architecture and how each component works in detail. The retriever module is the component responsible for finding relevant information from our knowledge base. Its effectiveness directly impacts the quality of our RAG system. Embedding process is an important part of RAG. Embeddings are numerical representations of text that capture semantic meaning. When we convert text to embeddings, similar concepts end up close to each other in vector space, even if they use different words. For example, automobile and car would have similar embeddings because they represent the same concept, despite being two different words. Modern embedding models like OpenAI text embedding or model from MTEB leaderboard generate high-quality embeddings that capture nuanced relationships between concepts. These embeddings are stored in specialized vector databases optimized for similarity search. Popular options include services like AWS OpenSearch, Google AlloyDB, Cloud SQL, Vertex AI Vector Search, Azure AI Search, Pinecone, and many more. Vector databases are designed to efficiently find the nearest neighbors to a query vector in a high-dimensional space. They use techniques like approximate nearest neighbor search to make this process fast, even with millions of vectors. The retriever uses several methods to find relevant information. Dense retrieval is one of them. This is the standard approach where the query embedding is compared to document embeddings using similarity metrics like cosine similarity. Hybrid search is another method that combines dense retrieval with traditional keyword search for better results, especially with rare terms or proper nouns. Re-ranking is a technique after initial retrieval. A more computationally expensive model re-ranks results based on relevance to the query. Multi-step retrieval is breaking complex queries into subqueries and retrieving information for each and then combining the results. The retriever's job is to return the k most relevant chunks of information, where k is typically between 3 and 10, depending on the application. The generator module is typically a large language model like GPT-4, Claude, or Llama. Its job is to synthesize the retrieved information with the original query to produce a coherent, accurate response. The way we format the prompt for the generator is really critical. A typical RAG prompt includes system instructions where we're telling the model how to use the retrieved information. It also includes retrieved context, the information retrieved from the knowledge base. It includes user query, which is the original question or instruction, and output format instructions, indicating how the response should be structured. The generator needs to understand which parts of the retrieved context are relevant and how to incorporate them into a coherent response. The fusion mechanism is how the retrieved information is integrated in the generation process. There are several approaches. One of them is early fusion. It's when the retrieved information is added to the prompt before generation begins. It's the simplest approach and what most basic RAG systems use. Late fusion is when the model generates a response first, then modifies it based on the retrieved information. Iterative fusion is when the model retrieves information, generates a partial response, retrieves more information based on that partial response, and continues the process. Adaptive fusion is when the model dynamically decides how much to rely on retrieved information versus its parametric knowledge based on the query type. With the understanding of these concepts, let's walk through a workflow to see how all these components work together. A user asks, what were the key outcomes of the 2025 customer survey study in our company? The query processing starts, and the query is embedded using an embeddings model. The system then searches a vector database containing articles, reports, documents about this report, and it retrieves the most relevant chunks about the 2025 customer study. The retrieved chunks are formatted into a prompt along with the original query. Then the generation occurs when the LLM reads both the query and the retrieved information and generates a response that accurately summarizes the key outcomes of the customer study. Then the response delivery occurs when the user receives an accurate answer based on the specific information about the study, even if the LLM's training data didn't include this information previously. This architecture allows for flexibility. We have an option to swap out different retrievers, generators, or knowledge bases depending on our specific needs. We're also able to extend the architecture with additional components, like query reformulation to improve retrieval, like answer verification to check for factual accuracy. We can add citation generation to track sources. We can also add feedback loops to improve future retrievals. Now we know the RAG workflow, it's really important to explore the business value and ROI of implementing RAG systems, why it matters, and what is the actual return on investment when implementing RAG systems. One of the most immediate benefits of RAG is cost efficiency compared to fine-tuning large language models. Fine-tuning a model like GPT-4 or Claude requires significant computational resources. We need specialized hardware, machine learning expertise, and time, sometimes weeks or months. The costs can easily turn into tens or hundreds of thousands of dollars for a single model. RAG, by contrast, requires no modification to the underlying model. We are using the model as is and simply changing the input by adding retrieved context. This means no expensive training infrastructure, no specialized machine learning expertise, faster implementation timeframes, and lower ongoing maintenance costs. RAG provides most of the benefits of fine-tuning at a fraction of the cost. Hallucinations, where LLMs generate false but plausible-sounding information, are one of the biggest barriers to the enterprise AI adoption. They create significant business risk, especially in regulated industries. RAG dramatically reduces hallucinations by grounding model responses in specific retrievable information. This improved accuracy translates directly to reduced compliance and legal risks, higher user trust and adoption, fewer resources spent fact-checking AI outputs, and more reliable automated processes. LLMs have knowledge cutoffs, so GPT-4 doesn't know about events after its training cutoff date. Traditionally, keeping an LLM current would require periodic retraining or fine-tuning, which is expensive and time-consuming. So RAG solves this problem very elegantly. When new information becomes available, we simply add it to our knowledge base. The model is able to immediately access and use this information without any retraining. This capability is particularly valuable for fast-changing industries like finance or technology, for organizations that regularly update their documents or policies, also for applications that need to reference current events or recent developments, for businesses with seasonal changes or frequent product updates. In many business contexts, especially regulated industries, it's not enough for an AI to provide an answer. We need to know where that answer came from. So RAG systems provide natural explainability because responses are based on specific retrievable documents. This means we're able to cite sources for any generated information. We're able to audit the retrieved process to understand why certain information was used. And we're able to trace exactly which documents influenced a particular response. We can also demonstrate compliance with regulatory requirements. This transparency is crucial for applications in healthcare, finance, legal, and other regulated domains. Every business has unique knowledge, terminology, and processes. Generic LLMs struggle with specialized domains because they lack specific knowledge or use terminology differently. RAG allows us to ground the model in our specific domain knowledge without expensive custom model development. This means the model is able to reference our internal documentation and use our terminology correctly. We can incorporate proprietary knowledge that isn't available in public training data and create specialized AI assistants for niche domains, and all of that with minimal investment. This way, we can maintain competitive advantage by leveraging our unique information assets. Some concrete ROI examples from practical RAG implementation in business are reduction in time to resolution, decrease in escalations to human agents, improvement in customer satisfaction scores, reduction in time customers or employees spend searching for information, and increase in employee productivity or decrease in customer time to purchase. The business case for RAG is compelling across almost every industry and function. The business case for RAG is compelling across almost every industry and function. It delivers immediate value while avoiding the costs and complexities of custom model development. Now that we understand the business value of RAG, let's explore specific use cases where this technology excels. These examples show how RAG is being used and applied across different industries and functions. Customer support is one of the most natural applications for RAG. Support teams deal with high volumes of repetitive questions that often have answers documented somewhere in the company's knowledge base. RAG-powered support systems help instantly retrieve relevant information from product documentation, frequently asked questions, and support tickets. They also generate personalized, contextually appropriate responses, handle complex multi-turn conversations by retrieving different information as needed. They provide citations for specific documentation for verification. They learn from new support tickets to continuously improve responses. So RAG-based support systems reduce issue resolution time and improve customer satisfaction. Researchers in academia, science, or medicine and business intelligence spend significant time gathering and synthesizing information from multiple sources. RAG-powered research assistants help search across research papers, reports, and databases using semantic understanding. They generate literature reviews and synthesize findings from multiple sources. They identify connections between seemingly unrelated research areas and extract and summarize key methodologies or results. These capabilities accelerate the research process and help identify insights that might otherwise be missed. Content creators, from marketers to technical writers, leverage RAG to produce more accurate, well-researched content. RAG systems for content creation generate first drafts in specific brand guidelines or style guides. They fact-check content against authoritative sources, summarize long-form content while keeping key information. They create consistent content across multiple channels and adapt existing content for different audiences or formats. Marketing teams using RAG increase content production efficiency while maintaining or improving quality. Recommendation systems benefit enormously from RAG's ability to combine user-specific information with broader knowledge. For example, they retrieve specific details about products, services, or content items, combine user preferences with detailed item information, explain recommendations by citing specific features or attributes, and handle cold start problems by leveraging detailed item descriptions. So e-commerce and content platforms using RAG for recommendations significantly improve conversion rates and user engagement. Some of the most powerful RAG applications are in specialized domains where general LLMs lack specific knowledge. Now you know key RAG concepts, components, and architecture. Let's recap the main points. RAG is a powerful technique that enhances large language models by connecting them to external knowledge sources. It addresses critical limitations of standalone LLMs. Knowledge cutoffs are overcome by providing up-to-date information. Hallucinations are reduced by grounding responses in specific sources. Domain-specific knowledge is incorporated without model retraining, and transparency is improved through source attribution. The core RAG architecture consists of three main components: a knowledge base of indexing documents, a retriever that finds relevant information, and a generator that creates responses using retrieved context. Whether you're a developer, an architect, a manager, or a business owner, understanding RAG improves your results when working with LLMs. The business value of RAG is in cost efficiency compared to fine-tuning, improved accuracy, up-to-date information, and domain customization. RAG is great across multiple applications, including customer support, research, content creation, domain-specific implementations in healthcare, finance, and engineering. Make sure to subscribe to my channel and like this video. Thanks for watching, and I will see you in the next video.
Your reality has changed. You're stuck in your career. You're either using AI or being used. Do you still believe success is guaranteed? You feel it's time to wake up. Old strategies don't work anymore. Welcome to the real world. It will never be the same again. You need to fight for your future. Learn to spot truth from lies. I will help you. Together, we will win.